Okay.
Excellent.
Okay, let's try again. Take two. Welcome to the seminar, everybody. This week we've got Xintao Luo speaking about short-time existence and uniqueness of Ricci flow. Please go ahead, Xintao.
Hello, everyone. Let's continue the proof of short-time existence and uniqueness of Ricci flow. We start with a quick review of the last time's talk. Last time, we introduced the notion of differential operator, which is a map depending on the derivatives of sections pointwise. The principal symbol and ellipticity is determined by the highest term of the linearized of the differential operator. And we show that the Ricci curvature is not an elliptic operator of Riemann matrix. By using these derivatives, Ricci detour flow is introduced, and it enjoys short-time existence and uniqueness due to its ellipticity. To recover Ricci flow from Ricci detour flow, we need to know the relationship between these derivatives and time-dependent diffeomorphisms. And last time, we had given the definition of time-dependent vector field. It means that for each time, there is a vector field on the manifold. The integral curve describes the motion along the time-dependent vector field. The velocity at the time t is just the vector at that time and at that position. Similarly, we have the definition of time-dependent tensor field. Now, we give the fundamental theorem about time-dependent vector fields. This is a corollary of existence and uniqueness and smoothness theorem of ODE. The map theta given in the theorem means that if at the time s, your position is at P, and your moving curve is the integral curve of V, then your position at time t will be theta TSP. Okay. Now we can use lead derivatives to compute the derivative of a time-dependent tensor field under a time-dependent flow. This is the proposition here. Let M be a smooth compact manifold without boundary and J be an open internal of R. Suppose that V is a smooth time-dependent vector field on M and theta to be the time-dependent flow, and A is a smooth time-dependent tensor field. Then we have the following formula. The first term, it means that A is fixed, while in the second term, the pullback map is fixed. Now we can show the short-time existence of Ricci flow now. Suppose that M is a compact Riemann manifold without boundary, and D is any phase symmetric connection of the tangent bundle. Then there is a positive number T and a smooth family Riemann matrix, which satisfy the initial value and the Ricci detour flow. Let theta be the time-dependent flow of V, and we write phi t to be the theta t0 by the fundamental theorem about time-dependent vector field. We had this. Okay. Now we let the GT to the pullback of G hat T. Then we will show that GT is the solution to Ricci flow. In fact, by direct computation, we know that for this one, we can take derivative to the first part and the second part. Then it becomes the two terms. And as for the Ricci terms, notice that the pullback and the Ricci is interchanged like this. And finally, we can show that since this is a Ricci flaw, so it's 0, and finally this term is 0. And the initial value is satisfied trivially. Okay, now we have shown the short-time existence of Ricci flaw by constructing a solution to Ricci flaw from a solution to Ricci flaw. To show the uniqueness of Ricci flaw, we need to recover Ricci flaw from Ricci flaw. By above computation, it suffices to find a smooth family of diffeomorphism phi t, satisfy the PDE. Here, GT is a given solution to Ricci flaw. To understand the PDE above where, we will introduce the pullback bundle and show that it is a solution to a harmonic mesh heap flaw. Now we introduce the pullback bundles. Suppose that M and N are two smooth manifolds without boundaries, and E is a smooth vector bundle over M. Then for smooth map F from M to N, we define the pullback bundle to be this. In fact, we can draw up, assume that M to N is a smooth map, and E is a bundle. Then M times E. We have two natural projections. Then we choose a subset of M times E such that this and this, from this to E and to N, and from this to M to N interchange. And it is a vector bundle, since that we can write it as the form this. And the bundle of E, the bundle E introduce the vector bundle structure to the F star E. And the bundle projection is just the restriction of the projection to F star E. Okay. Now we assume that there is a connection on E. We will define a connection on F star E as follows. For each P, we choose any frame of E, smooth frame of E on a neighborhood, and we define the derivative with respect to X is this. Notice that the choice of the connection, I mean that the choice of the coordinates is not influence the definition. Now we assume that E is the tangent bundle of M. In fact, for any vector fields X and any point in P and any point P in M, we obtain a vector in the tangent space of N by applying the differential of F to XP. However, this does not in general define a vector field on N. For example, if F is not surjective, there is no way to decide what vector to assign to a point in Q outside the image. If F is not injective, then for some points of N, there may be several different vectors obtained by applying df to X at different points of M. But now we can consider dfx as a section of F star Tn, and we see that df is a section of the bundle like this. Now we choose any symmetric connections on the tangent bundle of M and N. We can define the second fundamental form like this. Notice that df is a section of this bundle. So we can take derivative to df. And then for any two vector fields x and y, we define it to be this. If J is the Riemann matrix of M, we can define the Laplacian F to be the trace of the second fundamental form. Notice that when F is an immersion, then the second fundamental form of F here is just the second fundamental form we all know before. A straight proposition about the second fundamental form of the composition of smooth maps is given as follows. Suppose M and P are three manifolds, and we have two smooth maps from M to N and N to P, just like this. M to N. This is F, and this is F hat. Now we can consider the second fundamental form of F and the second fundamental of F hat, and the composition with its second fundamental form. The second fundamental form of the composition is given like this, or precisely, we take any P and SP, S and Y to be the vector field. It can be right at this. The proof of this proposition is quite easy. It's just to write it in any local smooth coordinates. And if J is the Riemann matrix of M, and F is a diffeomorphism, we can take trace of this formula and get the result. Okay, now we give an important example for our later use. Assume that F is identity map, but the manifold is using different connections, nabla and D. Now the second fundamental form F is just the difference tensor of the two connections. And if nabla is the Levi-Civita connection of a matrix G, then we know that how G is the second fundamental of F and the Vg is the Laplacian of F. Tau G and Vg, we have given this in the last time. Tau G is the D minus Laplace, and V. Okay. Now we can return to the equation given as before. In this equation, GT is a given solution, but the G hat and the phi t is unknown. But we know the relationship of these is given by this. Since the pullback of G hat is G, so the second fundamental form of phi t is 0, since the phi t preserving the matrix and therefore it preserving the connection. So the second fundamental form is 0, and we know that Laplace phi t is also 0. Now let Ft be the identity map of M, but with different connection. And we know that Vg hat t is the Laplacian of Ft. By the proposition about the second fundamental form of the composition to the following two maps, we can compute the derivative with respect to t of phi t like this. This is right Ft and this is phi t. Okay. We have known that Vg hat t is the Laplacian of Ft, and in this part, we're using the proposition of the second fundamental form of the composition, and we know that the Laplacian of phi t is 0, so it disappears. And finally, get this. So we let the composition to psi t. Notice that since Ft is the identity map, so as a map, phi t is equal to psi t. But now it's different because psi t is using the connection Gt and D, while phi t is using Gt and G hat t. We know that psi t is certified harmonic massive flow with the initial value to be the identity map of M. It's easy to see that harmonic massive flow is elliptic, but to apply the standard PDE on vector bundles, we consider the composing a phase smooth embedding. The embedding is always exists by the Whitney embedding theorem. Then by computation, we know that the composition satisfies the following PDE. When we take derivatives, since iota is always fixed, so it became this. And for this term, it's just the using of the proposition of the second fundamental form of the composition of maps. We have these two terms, and finally we know that it depends only on the first derivative and the map. Therefore, the harmonic massive flow enjoys short-time existence and uniqueness by the standard PDE theory. Now we can begin to show the uniqueness of Ricci flow. Let MG now be a compact Riemann matrix without boundary, and assume that G1T and G2T are two solutions to the Ricci flow with the same initial value. Now we claim that they are the same in the intersection of their domain. In order to prove this, we argue by contradiction. Suppose that therefore some t such that G1T is not equal to G2T. So we define the T star to the infinite of this set. Of course, it's larger than 0 since we have this. By continuity, we know that at this time, G1T star equal to the GT star. Let psi t to be the solution of the harmonic massive flow. Notice that the matrix and connection with the initial connections to be the identity map. So it follows from standard PDE theory that the solutions are defined on some time interval for some epsilon larger than 0. Moreover, if we choose the epsilon to small enough, then the above two solutions are diffeomorphisms in the internal. Okay. Then for the two solutions, we can define two Riemann matrix G hat 1 and G hat 2 by this. Then by the computation before, we know that G1 hat and G2 hat are two solutions of Ricci-Dieter flow with the initial value. We can repeat the computation here again. We know that psi t certify the PDE, and now we're using the composition. And finally, you get this. So it satisfies the Ricci flaw. And we introduce the identity map FT, and then by direct computation, we know that if this is 0, and finally this is 0. The computation here is totally set as before. By the uniqueness of the Ricci flaw, we know that G1 hard and G2 hard is the same in the internal. So these two solutions to the as the integral curves of the same time-dependent vector fields, and their initial conditions are the same. So therefore, the two integral curves must be the same. And then the matrix G1T and G2T is also the same, which contradicts the definition of T star. Now, we end this note by giving a sketch proof of solving strongly parabolic PDEs. Let M be a smooth manifold without boundary, and E be a smooth vector bundle over M. Choose any connections on tangent bundle of M and E, and let D be the induced connections on the mixed type of the tensor fields. And we assume that E plus is an open subset of E. Let P be the differential operator given by like this. Now we know that P is elliptic at U is equivalent to there exists some positive number C such that larger than the square of the length of H. Notice that the matrix of E is any matrix. Okay, we give the theorem of the hello?
Yes, we got you.
Okay. Now we give the theorem as follows. Assume that P is elliptic at one section U0, and then there is a positive number T larger than 0 and a smooth family of sections such that it satisfies the initial condition and satisfies the flaw here. Now we give the sketch of proof of this theorem. Without loss of generality, we can assume that initial condition is 0. Otherwise, we can replace U by U minus U0. And we're using the new differential like this. So we can assume that the initial condition is 0 now. Then for any positive number and any alpha less than 0 but less than 1/2, we define the two set and define the map like this. Okay, so the solution of this equation just to find the some U such that FSU to be 0. Now we define the U hat T to be this. Then we know that the FSU hat when T is 0, is always 0 now. So by continuity and the completeness of the manifold, we know that the norm of it, the norm of FSU hat will converge to 0 when S conversion to S0. Okay, let Ls be the linear rise of Fs at U hat. It means that S to be Fs in U hat. Okay, given any H, we can compute this. Notice that the B and C are two smooth sections, which depends on A and F. Okay, now my parabolic shelter estimate and parabolic maximum principle, we know that the norm of H is controlled by the sum of these two terms. And by parabolic maximum principle, we know that this is controlled by this. So finally, we know that Ls has a trivial kernel, so it is injective. Moreover, since the linear parabolic PD is solvable, so it is also surjective when S is sufficiently small. So we know that Ls is invertible when S is small enough, and okay, this must minus is also bounded. Then, by the inverse function theorem, we know that Fs is invertible on a neighborhood of U hat to a ball of radius R centered at Fs U hat. Notice that R is independent of S. In fact, F is Us to Vs. It maps the U hat to Fs U hat. And we know the differential at U hat is invertible. So we know that there is a neighborhood of this, are a diffeomorphism. So when we choose the S to small enough, we can get that the norm of the U hat is less than R. So the original point is in the ball of radius R. Therefore, we obtain that there must be an element U such that Fsu to be 0. So we get the solution of the strongly parabolic PDEs. Okay, we can end this talk today now.
You're finishing there, Xintao? That's the end?
Hello?
Hi, Xintao. Is that so you're finishing there? Is that right?
Yes, I finished today.
No worries. Thank you for that. So we have 24 minutes for questions, if anybody has any. So if I think I roughly see what's going on there, Xintao. But you basically have, so you have to set up these Helder spaces, but you have a compact manifold, and you can set up, if you have a metric and a connection, you can define these nice Helder spaces. And so you have, so when you say by parabolic Schauder estimate, you have that basically in these spaces on the manifold. You're not sort of referring to a more classical Euclidean Schauder estimate. Is that right?
In fact, the proof of this final theorem, I don't understand it very well. I just see the sketch of the proof of the notes of Richard Balmer.
I was going to say, you fooled me. You seem to understand it pretty well. Yeah, but basically this is happening. So these norms are with respect to these Helder spaces on your vector bundles, right?
Yeah. In fact, the two space is given like this.
Yeah.
So we use the natural norm of this.
Mm-hmm. Yeah. Okay. Yeah. And so you have so presumably you have a version of the Schauder estimate just working on equations when working in these spaces.
Is it the same Schauder estimates that Charlie proved in his thesis?
You mean this one?
I'm just saying, I think it's the same statement that Charlie proved in his thesis, which would be for equations, just for equations in vector bundles. Yeah.
Here, LS is a linear operator. So we can use the linear parabolic Schauder estimate now. Okay.
Right. Yeah. But I guess for linear equations, but on your vector bundles, right?
Yeah.
Yeah, I think that clarifies what I was worried about. Does anyone else have any questions? Feel free to jump in.
I don't know much about this topic, but does anything strange happen if we broaden our class of manifolds, non-compact manifolds, for example, with some growth conditions?
For the manifold is not compact. In fact, about the Pdes theory, only know the theorem about the compact manifold. For example, in the proof here, here we need a continuity and compactness. Yeah.
Yeah, so the proof as given doesn't work exactly for non-compact, but I wonder if there are straightforward modifications and conditions that we can put in place to get it working for non-compact.
There are some classical results that you can get for short-time existence for non-compact manifolds. They usually involve making some curvature bounds at infinity, like a bunch involving lower bounds on Ricci curvature and some sort of bounds on sectional curvature.
Yeah, presumably you run into a lot of issues, but depending on how many conditions you wanna place it. Okay, great. Well, thank you very much, Xintao. It's a very nice talk.
Thanks, Xintao.
Yeah. So I guess
thanks everyone.
Thank you very much. Cool.